So hi everyone, and good morning for wherever you are. And I'm Shafi Goloser. I'm the director of the Simons Institute, and I'm really truly delighted to welcome our speaker today, Javier Esperanza. Oh, no, it's
No.
Javier just
Try
taught me
again.
Esperanza.
No,
Esparza.
Esparza.
Esparza, okay. But I did it better before. And since 2007, Javier has held the chair of Foundations of Software Reliability and Theoretical Computer Science at the Technical University of Munich. He has held the chair of Software Reliability and Security at the University of Stuttgart and the chair of Theoretical Computer Science at the University of Edinburgh. Javier has co-authored a book on free choice Petri nets and a
Oh,
book
come on. You are going to read all that?
no, I'm selecting. And a book on unfolding approach to model checking, and it's published extensively in the fields of automatic program verification, program analysis, concurrency theory, and automata theory. So Javier is, as we said, they published a book, but not only that, contributed to the theory of Petri nets, was one of the initiators of the unfolding approaches to model checking, automata theoretic approaches to software model checking, and verification of infinite state machines. And more recently, he's turned to working on fundamentals of program analysis, verification of parameterized and stochastic systems. And Javier is also highly decorated. He holds an honorary doctorate in informatics from the Masaryk University of Brno, and he's a member of the Academia Europaea and recipient of ERC. And today's talk is entitled, a wonderful title, Back to the Future, as we see in the cover page, a fresh look at linear temporal logic. I just want to say a word before we let Javier take the stage and welcome him on stage, is that a word about the series. This is a series named Richard M. Karp Distinguished Lecture Series, and we established this series in honor of the Karp, who was the Simons Institute founding director. And as we all know, he's really the father of theoretical computer science, formulating essential problems, contributing stunning results in many areas of computation complexity and algorithms, a true visionary. And we are very grateful to his many contributions. And this series is a small token of our appreciation. So please help me welcome Javier, and I'm looking forward to his talk. So,
okay, thank you very much. Thank you for the introduction. It's not every day that you are introduced by a Turing Award winner. This goes straight to my CV. And so thank you for the invitation as well. So today I want to talk about a fresh look at linear temporal logic. And this is joint work with Jan Kretinsky and Salomon Sickert, as you can see here. And I think it's fair to say that actually they have a larger share in this work than I have myself. So now and then here in Munich, I have to teach a first year course on discrete math, and I have to introduce students to logic. And I like to tell them that logic is what you do when you go to a bookshop. You go to the section on fantasy and science fiction, you pick a book at random from the shelf, you open it, you read this sentence: if all Bandersnatches are Borogos and all Borogos are Slithi, then all Bandersnatches are Slithi, and then you say true. And of course, the paradox is, how can you say that this sentence is true if you don't know what you're talking about? And after a moment of reflection, of course, you notice that the meaning of this sentence depends on the meaning of all its words, but the truth of this sentence does not depend on the meaning of all words. It only depends on the meaning of some words. In particular, this sentence is true whatever X, Y, and Z are. So this is my favorite definition of logic. Logic is the subject of identifying true statements in a language of which you only know a few words. And this also gives you a very easy way of defining what's temporal logic. Is the logic where the words you know in the language are the words of propositional logic. So you know what and or and not means and if then. And then you also know a few words about temporal aspects of language, right? Or about temporal words like today, tomorrow, eventually, or never. Temporal logic started as a branch of mathematical logic, started to be studied by mathematical logicians at the end of the 19th century. But I think it's fair to say that it remained a rare flower, an exquisite flower, not known to many people until 1977, when Amir Pnueli proposed it as proposed temporal logic as a language in which to specify properties of concurrent and reactive systems, and in which to reason about them. And I know that Orna is in the audience. This is a very nice picture of Amir I like very much, and also with Orna there. So the idea, what Amir observed, of course, is here you have some examples of specifications of reactive systems. And what Amir observed is that they fit exactly this pattern. You have some technical jargon you know nothing about, like the rec close state, or what the hell is an ADT, or well, probably you can guess what the OK button is, but maybe you don't know for sure. And all this is linked with terms that come from temporal aspects of language, from temporal words, right? Like all the things that you see there in bold face. So this is the temporal logic that Amir worked with almost then throughout his career, linear temporal logic, which as any temporal logic extends propositional logic with temporal operators. The syntax we are going to use today is not the standard one. It deviates slightly from the standard one, so let's go through it. So first you have just propositional logic, but propositional logic in negation normal form, where you can only have negations in front of atomic formulas, atomic propositions. Then you have the standard temporal logic operators that probably many of you know about. This one, which means next phi1 with semantics tomorrow phi1 will hold. And this one, phi1 until phi2, with semantics, phi2 holds at some point in the future, at some day in the future, and until then, every day satisfies phi1. So specifically important for this talk is the weak until operator, which is less known, and which is, of course, it's called weak until, so it's similar to until. The idea is that phi1 weak until phi2 holds if phi1 until phi2 holds, or if phi1 holds forever. So this means it is no longer necessary to have a point in the future at which phi2 holds. So this is the logic we are going to use today, the syntax we are going to use today. Some of you, those of you who know quite a bit about LTL, they might ask, why don't you have these operators? And the answer is, don't worry, you can imagine that they are there, but for reasons of presentation, I am not going to have them. And then something that we also have to spend a couple of seconds talking about are past operators. So you could also add past operators to this logic. For example, instead of tomorrow something will hold, yesterday something holds, that would be another operator, or since instead of until. And in fact, Amir Pnueli used these temporal operators in quite a few papers. When you have those temporal operators, additionally, then the logic is usually called past LTL. So past LTL contains both past and future operators, and future, the standard LTL, the name LTL is reserved usually for the case in which you only have the future operators. And an important thing that I can already tell you is that both are equally expressive. So for every formula with past operators, you have another one which is equivalent to it without past operators, which is a very nice result. And then there are two abbreviations, which probably most of you are familiar with, because this is what you see most of the time in examples, in papers, and so on. This operator, which is read eventually phi or finally phi, which can be expressed like this, and which means there is a point in the future at which phi holds, and then g psi, always in the future, phi holds. And just remember that f is linked to until, and G is linked to W. Okay, so this is just to show you how fantastically now you can formalize specifications in terms of temporal logic. Don't worry, you don't have to understand any of this. It's just to give you a visual impression. And then we move to the next point, which is what did Amir did after he published his paper, the first paper on temporal logic. He embarked into a 10-year, actually a bit more even, research program, where, and in the second part of that research program, he was accompanied by Zohar Mana. And the program was about developing temporal logic as a specification or reasoning language for verifying, for specifying and verifying reactive systems. And it culminated in these two books, as you can see, published in 92, 95, and there was even a third volume, which was unfortunately not finished and not published, and which was the spine of this research program. So the spine of this research program was what is called, or what actually Zohar Mana and Amir Noeli called the safety progress hierarchy, which is a classification of the properties of temporal logic. Okay, and there are these classes in the hierarchy, and they give different characterizations of these classes, in particular a syntactic characterization in terms of syntactic classes of formulas, right? And it was, they introduced this classification in past LTL, so the classes of formulas were formulas including past operators. But, you know, they saw, for example, they showed that every formula is equivalent to a formula of this form, where phi I and psi I contain only past operators. And, you know, they had this hierarchy, and the idea was then to introduce proof rules for the different classes in this hierarchy. You don't have to understand this, but these are taken from the book. And you can see examples of proof rules here, actually with a different notation. This would be a G, and this would be an F, but never mind. The important thing is that this was, what they wanted to do was to develop proofs of concurrent programs. So actually, this was a logical endeavor, a logical enterprise, and the goal was to produce proofs, probably also proofs that could be also produced by humans, so not necessarily automatic proofs. So, of course, a key result then for this research program is the normal form theorem. The fact that every formula is equivalent to a reactivity formula, to a formula in this form. Okay, so this is a central result in the ideas of Mana and Noeli. So let's look at the proof of this normal form theorem. The proof was presented in this paper, but it was not presented in the paper, it was announced in the paper. In the paper, you only find this. And in fact, if you look for it in the book or in some survey papers that Mana and Noeli wrote, you will not find it there. It is always, you find always something like this proof is out of the scope of this paper or of this book or of this survey. So in fact, if you want to find the proof, you have to go directly now to the PhD thesis of Lenore Zak that you can find in the web. And let's have a look at this proof. So Zak starts with a past LTL formula and then translates it into a counter-free semi-automaton, whatever that means. Don't worry, we will not be using that. Then she invokes the Cron-Rhodes decomposition theorem to go from the counter-free semi-automaton to a star-free regular expression, and then translates the star-free regular expression into a past LTL formula in normal form. Okay, so about half the thesis, you could say, is devoted to the proof of this theorem, and moreover, this last step has a non-elementary blow-up. Okay, so things probably get a bit better because of this paper, which was published much later, as you can see, and there Oded Mahler probably find something, the paper is about something else, probably you can derive a triple exponential bound from there. But in any case, it's looking pretty bad, right? It's looking pretty bad. And the problem is that since then, nobody has had a look at this again. And I must say that I find, even though there is no lower bound, and I find this pretty remarkable, right? So you have here a central result in the main research program of a Turing Award winner, and nobody has tried to find the matching bound or see whether there is a faster algorithm. Okay, so actually very, very remarkable. And why is that? Well, I think that you could say that probably that the culprits are these two guys, are Vardy and Volper, who publish in Leaks 86 this paper, presenting the automata-theoretic approach to automatic program verification. I think there is some debate whether they were the first to do this, or whether former work by Amir on Tableau could also be called automata-theoretic approach. Who cares? Definitely they were the guys who discovered it last. And after this work, the automata-theoretic approach stayed discovered. Okay, and the automata-theoretic approach translates the formula, for example, a formula like this, into an omega automaton, typically a Bush automaton, and then essentially you throw the formula away. Everything else is done with automata-theoretic algorithms. So this means that you don't need to have proofs anymore. Proofs are replaced by computation. So you have no need for hierarchies, proof rules, axiom systems, or anything. Okay, and the automata-theoretic approach was so successful that actually it, people probably thought, or even Amir himself, who knows, thought, well, this logical approach actually is not so exciting. Maybe we should do more exciting things on the automata-theoretic side. So in a sense, and this is of course kind of a slogan, this approach demotes LTL to kind of syntax for automata. So you write your LTL property, you transform it into an automaton, and then you can safely forget about LTL. So, and during the next decades, the automata-theoretic approach was extremely successful. So it was implemented in very sophisticated and very successful in industrial strength tools. It was extended to the verification of probabilistic systems, where you want to check whether a property holds with probability 1 or with probability more than a certain threshold. And it was also applied or extended to reactive synthesis. So instead of worrying about checking whether an existing program is correct, you want to automatically derive the program from the specification. And there has been quite nice successes in this area. In particular, there is a nice reactive systems competition that has been going on for several years. Okay. However, these developments come with an associated challenge. So reactive synthesis, the application to synthesis, requires to translate LTL into deterministic automata on infinite words, contrary to the case of verification where non-deterministic automata are also fine. And probabilistic verification requires to translate LTL, not necessarily, you could also, deterministic automata are also fine, they require a little bit less, you could do with limit deterministic omega automata. So don't worry if you don't know what that is, we will come to that point later. The point is, as you know, that deterministic automata tend to be larger than non-deterministic ones, right? And on the one hand, on the one hand, we have the theoretical challenge, whether this is at all possible. And this challenge was solved by Safra in 1988, who gave a determinization procedure for omega automata, and by Moshe and Kurkuvetis and Yanakakis in 95 later, who gave a limit determinization procedure for omega automata. So the theoretical challenge is solved, but then you have the algorithmic challenge, because as I said, deterministic automata have this bad habit of being much larger usually than non-deterministic ones. And in fact, these translations have a double exponential blow up, contrary to the case of non-deterministic automata, where the blow-up is only single exponential. And also they are monolithic and very combinatorial. Monolithic means that, okay, you define the automaton in one go. You say, okay, the states of the deterministic automaton are just these mathematical objects, right? And for example, in the case of Safra's deterministic automaton, these states are trees of sets of states of the original automaton. And of course, there are very many trees of sets of trees of sets of states when you have a deterministic automaton of a few, even of a few states, right? And the problem is that this combinatorial explosion, it's actually quite hard for implementations to deal with. So there is an algorithmic challenge which is still going on, coming from, and it's been going on for probably more than 20 years. So just to give you an example, this is, for example, taken from a paper in 2016, right? And you see here some formulas which are pretty small. And here you can see how the deterministic automata using suffrage construction grow in the number, so the number of states of the automata. As you can see, this looks pretty bleak. So you have all seen, I hope, the movie Back to the Future, right? So you can imagine you are now McFly, who has got into computer science, as is asking, how can I improve these translations into automata? How can I do better in the future? And then Doc comes and says, yeah, we have to do better in the past. We have to go back to the past and repair this problem with the normalization theorem. Right, and McFly says, "Why? What is the connection?" And Doc answers, "No time. I'll tell you later. Just go." So they jump into the DeLorean and they go to the 1980s, back to the 1980s, to the safety progress hierarchy, and to this problem that the blow up is non-elementary. So the first thing they do is to observe that there is another hierarchy of LTL formulas, and let's call it the alternation hierarchy, okay? And it's actually very easy to define. It's very similar to the polynomial time hierarchy, and although it doesn't have to do with complexity, but the idea is that the class sigma 1 is the class of formulas where you only see until operators. You know, remember that we had, so next operators you can always have, and remember that on top of those we have until and weak until. So here we only have until. And oh, this should be pi 1, sorry, there is a typo there. Pi 1, there you only have weak untils. Delta 1, Boolean combination of sigma 1 and pi 1. Sigma 2, at most one alternation between u and w, and the outermost operator is an until. So you go from until to weak until. Pi 2, you go from weak until to until. Delta 2, Boolean combination of both. Okay? And well, these two look very similar, these two hierarchies, okay? And then in fact, Chankman and Pnueli in 92, they had already proved that in fact these two hierarchies coincide, or almost prove it. There is a nice paper by Pelanek and Straychek in 2005 giving, spelling it out. Okay, so actually instead of considering this hierarchy, you can consider this one, where notice all operators now, we only have future operators, we have got rid of the past operators. Okay, so now the normal form theorem becomes every formula is equivalent to a delta 2 formula. But we still have, if we try to, if we apply the results or the procedure of Lenard-Zak, then we get this non-elementary blow-up. So let's demystify normalization, and let's see that, let's prove that actually all this is completely overblown. There is a much simpler way of proving this theorem. And let's do it by example. So let's consider a formula where we have two alternations, right? So you have f, g, f, and remember that f is associated to until, g is associated to weak until, so here you have two alternations, okay? So let's do the following. Let's look at the innermost alternation, okay, which is this formula. And within that formula, let's look at the inner part, which is this, okay, the blue part. And now, let's consider two cases. Let's consider the case where this innermost blue part, right, holds infinitely often. So assume that I tell you, I give you the additional information. I am only considering words where this formula holds infinitely often. And then we have case 2 where the formula only holds finitely often. Okay, let's consider the first case. Here we have this formula. This formula says it is always the case at every day from now on, either B holds or there is a point in the future at which C holds. So now imagine that I give you the extra information that if C holds infinitely often, it is infinitely often the case that some point in the future satisfies C. In particular, this means that C itself must hold infinitely often. And therefore, since this is an OR, this means that the formula holds. So this means under this condition, this formula is equivalent to true. And now let's consider the other case where FC only holds finitely often, right? Okay, remember what this formula says. This formula says it is always the case that B holds or at some point in the future C holds. Okay, if FC only holds finitely often, then in particular C also holds only finitely often. This means there is a point in the future such that from that moment on, C never holds again. For example, imagine C is, there is a pandemic, so that would be fantastic, right? There is a point in the future such that there will never be a pandemic again. Well, in that case, you know that if I want, so I know that if I want to make this formula hold, from some point on, I will always have to make B hold, or the only possibility is to make B hold from some point onwards. And this means that this formula is equivalent to B or FC holds until I reach that point at which GB holds. And that point must come because I am working under this assumption. Okay? Good. If you have got this, essentially you have almost proved the normalization theorem. Because what's happening here? Here we are saying this formula under this condition is equivalent to a formula without any alternation. And this formula, where we have an alternation of the form WU, we have transformed it, or is equivalent under this condition, to a formula of the opposite polarity, right? Now we have a U as top operator and then a G here. And now, as you can imagine, well, right, I hope this is an aha moment for you. If you have a way of reversing the polarity, you can get rid of alternations. Okay? So let's try to make this work, right? So we start with the formula, and then we say, okay, either GFC holds or GFC does not hold, right? So this is just a logical equivalence using only propositional logic. And now I look at this innermost alternation, right? And what do? I replace there this by true. And now some of you, some alert should be going in your brains and saying, hey, you cannot do that. And you are partially right. I cannot do that. And why not? Because of the reference point of these two formulas. This formula here refers to the origin of time. But this formula here refers to a different point. The origin of time, if you want, is a different one. It is the point at which, for example, this A holds. Okay, it is referring to a different point in time. If you didn't get this, don't worry very much, because the only important thing is you cannot do this in general. You cannot, if you have this hypothesis out here, you cannot take a subformula and replace it by an equivalent formula. It would be fine if you would put the hypothesis there, okay, at the right point. But now comes the second aha point, namely that no, this is correct. Actually, you can do this in this case. And why? Because this is not an arbitrary formula. This is a very special formula. It is infinitely often C. And if infinitely often C is true at some point in time, it is true at any point in time. Okay, it doesn't matter where you put the origin of time. It will still be true. And that's why you can really do this. You can put this hypothesis out here, and you can replace here these subformulas by equivalent formulas. This works. And now we are done, actually, because we now have here, the formula we have here is already a formula with only one alternation. In fact, we can clean it up a little bit. Sorry, this one not yet, but after we replace the innermost formula by this one, what we did before, it is, right? And if we clean it up a little bit, this is what we get. And now this is a formula with only one alternation. You can convince yourself because here you see an until and a G, but that's the only alternation you see. And here you also see only one alternation and so on. Okay. If you want, we have done the triple somersault. Let's do in a second. Let me show you that this also works with a four-tuple somersault, right? With not a four-tuple, sorry, a quadruple somersault. Let's do a quadruple somersault with F, G, F, G. And let me just go quickly through the steps. We look at the innermost alternation, and within the innermost alternation, we look at the innermost part. Then we consider two cases. In this case now, since the innermost part is GD, we consider the case that FGD holds and the case that not FGD holds, right? And then again, we are going to replace these things by equivalent things under this hypothesis. In this case, this is what we get, okay? You remember before we got true, and now we get here false, and we got something a bit more complicated, and now we get this, right? And in fact, in this way, we have already found an equivalent formula with only this part that still has to be handled. Now we only have to do a triple somersault here, okay? And again, now we look at this. We look at the innermost alternation, and within that, we look at the innermost part. We consider now, again, two cases. The case where, this is the innermost part, and we consider the case where that holds infinitely often or not. This is what we get. And now we replace the red part. Once we will replace this one, so we will be able to replace the part above by true, and below we have to replace by this thing. And then if we clean it up, this is finally what we get. Okay, that's it. You don't need any counter-free automata. You don't need any regular expressions. And which blow-up do you have? Well, for that, we can go to this closed form expression, which is a little bit more technical than what I just showed you and that you can find in these papers, right? This closed form expression tells you that the formula phi is equivalent to this thing. Okay, and now let's look at this thing and try to interpret it. So here we have a big disjunction over all possible subsets of U subformulas, of until subformulas, and all possible subsets of weak until subformulas of the original formula. Okay, there is an exponential number of ways of choosing these subsets. This is going to give us an exponential number of disjuncts. And what is the role of these sets of formulas, of this M and this N? So the idea is that intuitively, these are the formulas that hold infinitely often, for which GF holds, and these are the formulas where FG holds. So you are considering several cases. You are considering the case where this set of formulas M holds infinitely often, and this set of formulas N holds almost always. And then a different case corresponding to another choice of M and N, and then a different choice and a different choice. Okay, and this gives you a disjunction with an exponential number of disjuncts. And now for each choice, for each way of choosing M and N, what do? Well, you have this conjunction telling you that all the formulas in psi hold infinitely often. And there is a technical point here because this formula is not psi, it is some psi prime. We don't have to get into that, right? All the formulas in N hold almost always, okay? And this is the formula that is equivalent to the original one under the assumption, okay? And now you do the simple little bit of math, right? So here you have a linear number of conjuncts, and each of the conjuncts has linear length. Here you have an exponential number of disjuncts. This formula here can have exponential length. What you get is exponential length. So not a non-elementary blow up, not a triple exponential blow up. You just get a single exponential blow up, which is not worse than bringing a SAT formula, a Boolean formula, into conjunctive normal form. Okay, so now back from the past. And if you remember the movie, when we come back from the past, the present has changed, right? Because of what we did in the past. So has the present changed? Is our algorithmic challenge going to be solved, at least in a certain way? Well, remember the first part of the algorithmic challenge, which was to go from LTL to limit deterministic Büchi automata. And the algorithm that was available for that before we moved to the past was this algorithm by Kourkoubetis and Giannakakis. We come back from the past and we find it now replaced by a different algorithm, okay, which goes as follows. I mean, the formula is first normalized, and then the formula is transformed into a limit deterministic Büchi automaton. Why did nobody think about something like this, think of something like this before? For the simple reason that nobody thought this could be useful, because this step was so costly that it doesn't matter what you do after it. But now we see that this step is not costly. Okay, so we can now think about that. Okay, and how does this look like? So I don't have time to give you to get into technical details, but let's see if I can give you the gist of the idea, at least convince you that this is a very natural way of doing things, so that you are inspired and have a look at the paper. So first of all, of course, I haven't told you what is a limit deterministic Büchi automaton. So first of all, well, I hope you will know, at least most of you, what's a Büchi automaton. If not, it is also not that essential. But what is a limit deterministic Büchi automaton? So it is an automaton which has two components, the initial component and the accepting component. And the accepting states, they are only in the accepting component. Okay? And both components are deterministic. So this means that the only non-determinism is in these transitions, because you could have, for example, this transition could be labeled with an A and the jump also with an A, right? And these are jumps that bring you from the initial component to the accepting component. Now, even if you don't know what a Büchi automaton is, probably it is clear for you that in order to accept a word, you are going to have to jump. If you stay here there are no accepting states, you will not accept any word. So you have to jump. But the only non-determinism that you are going to have in a run on an infinite word is when to jump. Okay, so that's the only thing that is non-deterministic. You choose the point at which you jump. By the way, this is what helps you. I told you that a limit deterministic Büchi automata helps you in probabilistic verification, and I can give you an idea of why that's the case. In a normal Büchi automaton, if you take a word, if you pick a word, there can be an uncountable number of runs on that word, because the word has infinite length, and at every moment you can branch. Okay? In a limit deterministic Büchi automaton, there is always only a countable number of runs, because the only thing, the run is completely determined by the moment you jump. Okay, so if you say I'm going to jump after 6 steps, then the run is completely determined by that. And this means now that if you imagine that the set of runs on a word has a certain probability which is not 0. In the case of a normal Büchi automaton, since you have an uncountable number of runs on that word, you may split that probability so that each run gets probability 0. There are uncountably many. That's no problem. But if you only have countably many, if you have to distribute a non-zero probability into a countable number of runs, then at least one run has to get a non-zero probability. And that's something that you can exploit in order to do probabilistic verification very well. Okay, in any case, now that I have argued why this could be interesting, how are we going to go from a formula like this is the formula with the two alternations, right, to a limit deterministic Büch automaton? So first we normalize, okay? And in fact, this part is going to be easy. Let us concentrate just in giving a limit deterministic Büch automaton for that part, okay? So we have to map essentially this thing to something like that. And now that we know that the meaning of jumps, then there is a very natural mapping, right? This part of the automaton maintains the formula that must hold at the moment at which GB starts to hold. Everything here goes around when is this formula going to hold, at which moment. That's the non-determinism, right? The automaton is going to guess the right moment to do the jump. So it will guess the point at which GB starts to hold. And then once it is here, it will check that this conjunction holds. The formula that must hold at the point at which GB starts to hold, but essentially that's a formula without alternation, right? And the formula that must hold always hold, which is also a formula without alternations. And for those, it is easy to give deterministic automata. So that's why this thing works. And here you can see a bit of size reduction, right? Before you had to use, the probabilistic verification was done with the Safra construction. So these are the numbers you had to deal with before. And these are the numbers you have to deal with the new construction. You have to deal with in the new construction. So now what about the other part? Going from LTL to deterministic automata, in this case to deterministic raving automata. Before we went to the past, this was the algorithm that was there. And now after we come from the past, this is the new algorithm. We first normalize, then we transform the normalized formula into something called a very weak delta 2 alternating Büch automaton. And then we go from there to a deterministic raving automaton. So let me give you an idea. This is going to be actually a part which is only for the people who are know a bit more about automata theory and LTL, right? Let me give you an idea of how to go from here to there and from here to there. Well, it is well known that you can transform an LTL formula into what is called a very weak alternating Büch automaton. And this is an automaton I am using the DNF normal form for this, so to speak. It's an automaton with which can have universal transitions, okay? And what that means is that in the case that B does not hold, what this means is that you can go from this state, the automaton splits into two, one copy goes here, and the other copy stays there, stays in the same state, and this continues, and maybe the automaton will split again and again and again, okay? The run of the automaton on a word is going to be a tree. So what happens after the delta 2 normalization? The important thing is that, as you can see here, you can have alternations between accepting and non-accepting states. Non-accepting, accepting, non-accepting, accepting. You can have arbitrarily many. After delta 2 normalization, you have at most one alternation in every path of the automaton. So if you start with a non-accepting state, all that can happen is that at some point you have an accepting state, and from now on, everything is accepting, okay? So what you can do is translate your LTL formula into a disjunction of this automata where each path has only one alternation. And that allows you to prove a lemma. I am not going to get into it, right? Which very much simplifies the condition that the run has to satisfy in order to be an accepting run. And using that lemma, you can basically go from the alternating automaton to a deterministic Bucci or co-Bucci automaton, depending on which formula you start with, using what is called, or a little reformulation of what is called the breakpoint construction, which is a straightforward construction. I am not going to get into the details of that, but the thing that you can keep in mind is this. Instead of the states being trees of sets, now you move to another construction where the states are pairs of sets. And the combinatorial explosion is much more manageable. Pairs of sets are much easier to deal with than trees of sets. That's the key point that allows you to do this. All this is, by the way, implemented. And you can go, you can, for example, start trying these translations before I finish this talk by going to the online demo at this URL. This gives you all the translations into automata, from LTL into automata. And this other tool, which equally, you can also start trying out before this talk finishes, uses all this to do reactive synthesis, uses these translations and other techniques in order to do reactive synthesis. And I just want to give you a visual impression of what this means. So here you have, I hope you can more or less read it. Here you have a set and a specification, which is telling you which property must be satisfied between about the relation between inputs and outputs to a system. So if you imagine a system where inputs come and outputs are produced, inputs come and outputs are produced, right? Then you have to, you define a certain relation on how these things have to evolve in time by LTL formulas. And then by clicking a button, you obtain this controller for this specification, which is correct by construction, and is in this case is going to take just 1 second or something like that. I think that's all I wanted to say, because also it's I have to wrap up. So this talk I called a fresh look at LTL. And why that? Well, imagine you would have to rewrite the book on SAT without using the conjunctive normal form, because nobody had thought about that. So that would be a nightmare. Imagine you have to rewrite the book on first order logic without scholemization. So I think that in a sense, that's what happened to LTL. We were not able to use the delta 2 normal form, or we didn't think too much about it because we thought it was so expensive. So I would like to just encourage you to think about all these things, right? All the things that that you have done with LTL in your papers, and think again, oh, could I simplify what I did by normalizing first? Because now normalizing is not expensive.
So,
and that's it. Thank you for your attention.
Javier,
oh,
thank you very much for a wonderful talk. There's one question here. In this amount, probably
okay.
More than
is
everybody.
there an exponential?
Is there an exponential lower bound for the normal form, or is it conceivable that one can still do better?
We don't know.
That's the question here.
So we don't know. So start trying. We think, of course, we conjecture that there is an exponential lower bound, but we are not sure. And in fact, we have been.
We have 1 minute.
Yeah.
If there's more questions.
I can ask a question.
So go on. Sorry.
For probabilistic model checking, Javier, there is also the Kurbet-Yanakakis exponential construction from Bucci automata to deterministic in the limit.
Yeah.
It is based on subset constructions. You don't need to do SAFRA to do probabilistic model checking.
That's correct, but I couldn't show you any experimental results compared to that one, because nobody has cared to implement it, as far as I know.
Why?
And also, that's a very good question, but also there is another point. The construction of Kurbet and Yanakakis, you can only apply it for qualitative model checking. If you want to show that something holds with probability 1, it does not work for quantitative. Our construction also works for quantitative. And in fact, if you replace the raving automaton by the limit deterministic Bush automaton, then what you have to do from that point on is exactly the same. So you don't need to reprogram to re-implement Prism. You just replace the automaton by the new one and use the same algorithm. Okay, so that's what made it possible for us. Also, we have Salomon Seeker has experimental results on doing probabilistic verification in this way, reusing Prism. You don't have to re-implement it.
I see. Okay, thank you.
Anybody else? I think Thomas, or you just?
Yes. So thank you very much, Javier, first for this wonderful talk. I just wanted, so your explanation showed how you can improve on the understanding of temporal logic, and now you don't need really automata anymore. But my question is, whether do you gain any new insight on some automata construction? I mean, everybody doing automata would like to do Safra construction just with 2 pairs of sets. Or do you have any things that goes in this direction?
Well, of course, no, I'm not saying that you don't now, I'm not going to make the same mistake again, right? I would say we did that mistake before when we forgot about LTL. Then we ran into problems because, the automata were very big. And now what I claim is that we had the way to move forward is to go back to LTL and introduce logical techniques again. Look at them again. Do not just ignore the mode LTL to just a specification language, right? Well, once you do that, yes, all our new constructions, we are giving new translations of LTL to limit deterministic Bush automata and of LTL to raving automata. We are reusing, the part that is new, if you want, or a part that is new is the normalization. That's a logical proof. I don't know how to do normalization with automata. Probably, of course, there must be a way, but I don't know how to do it. And then there is the point of, once you have the normal form, moving to an automaton. And for that, of course, you reuse things that you have learned. But the idea is that we can, for example, replace Safra's construction by something that is much simpler. It is the breakpoint construction, essentially, right? And we all know that the breakpoint construction is easier than Safra's construction.
Thank you very much. And I think we need to wrap up, but a really terrific talk, and maybe we can clap for you virtually.
Thank you very much for listening and for your patience. Yeah.
Thank you very much for your.
Okay. Bye-bye.
Bye-bye.